We're finally ready to introduce quotient groups. Today, we'll go over what a quotient group is, we'll prove that they're actually groups, we'll prove a very important theorem about them, which is that they are homomorphic images, and we'll see a couple examples. There are chapters in the description if you want to skip around the video, as well as links to relevant lessons introducing homomorphic images, normal subgroups, and coset multiplication. To construct a quotient group, we need a normal subgroup. So let H be a normal subgroup of a group G, and let G/H be the set of all cosets of H in the group G. This is the quotient group of G by H. It's also sometimes called the factor group of G by H. Sometimes it's read G mod H. So this thing, G mod H, this set of all cosets of H in G, with the operation of coset multiplication, is a group. And again, it's called a quotient group or a factor group. Let's begin by proving this set of cosets of H in G with the operation of coset multiplication is a group. First, it's obviously closed because if we take any two cosets of H, HA and HB, and multiply them together, by definition of coset multiplication, we just get another coset of H, HAB. So indeed it's closed. Let's move on to the main three properties of groups, which is associativity and identity and inverses. For associativity, if we have HA times HB times HC, so these three cosets multiplied together with these two grouped together, by definition, HB times HC is HBC. That's by definition of coset multiplication. But then HA times HBC, by definition, is HA times BC. But by the associativity of the group G, remember that A, B, and C are all from the group G, by its associativity, this coset, HA times BC, is the same as HAB times C. By definition of coset multiplication, that's the same as the coset HAB times the coset HC, which is the same as HA times HB times HC. This last step is again an application of the definition of coset multiplication. In total, we were able to get the parentheses from HB times HC to HA times HB, proving associativity for coset multiplication. In the set of all cosets of H, there is of course an identity element, which is HE. That's just the set H itself. It's the identity element of this set because any coset HA times the coset HE will be equal to HAE. But AE is equal to just A. So that's HA. We know that AE is A because E is the identity of the group G. So AE will have to be A, thus establishing that multiplying by HE on the right does not change the coset. The same thing happens on the left. If we multiply by HE on the left, we're still just left with the same coset. It doesn't change anything. So indeed, this is the identity element of the set, HE, or just H itself. I'll take this moment also to point out we're using right cosets here. We could do all of this again in terms of left cosets. It would work out the same. However, we really don't need to, especially because H is a normal subgroup, and in normal subgroups, left cosets are the same as the right cosets. Finally, we must show the existence of inverse elements in the set of all cosets of H. The inverse of the coset HA is simply the coset HA inverse. We of course know that A has an inverse because A is an element of the group G, so we can take its inverse and get A inverse. And we know that this is true, that the inverse of the coset HA is HA inverse, because if you take HA and multiply it by HA inverse, by definition of coset multiplication, you get A inverse, which is the identity HE. The same thing happens if you multiply by HA inverse on the left. You just end up with HE. So indeed, the inverse of any coset HA will be A inverse. That establishes that G mod H with coset multiplication is a group. Remember, H is a normal subgroup of G here, and this is typically called the quotient group of G by H, or the factor group of G by H. What makes the quotient group so important is that it's actually a way of constructing the homomorphic images of the group G. Indeed, the quotient group of G by H is always a homomorphic image of G, and this is really easy to prove. To prove this, we need a surjective homomorphism, a homomorphism from G onto the quotient group of G by H. So let's let the function f map G onto the quotient group of G by H. And f is defined like this, very simply. F of x, f of some group element x, equals the right coset hx, the coset that contains the element x. It's trivial to show that this function is surjective. Any element from the codomain will look like this. It's a right coset of h. And so, indeed, if you just take that element x and put it in the function, by its definition, you're going to get that element from the codomain. So for sure, it is a surjection. This is a function onto G mod H. Then, to prove that G mod H is a homomorphic image, we simply need to show that this function is a homomorphism, which means it must preserve the group operation. And that is done very simply here. F of xy, x and y come from the group G. By definition, f of xy equals the coset hxy. By definition of coset multiplication, this equals hx times hy, which by definition of the function is f of x times f of y. So indeed, this is a homomorphism, and it's a homomorphism onto G mod H. So we see that G mod H, or the quotient group of G by H, is a homomorphic image of G. Like I've said, this is also sometimes called a factor group because it actually lets us at times factor out an undesirable property of the group G. We can construct a homomorphic image specifically to exclude or factor out some undesirable property in different contexts. And we'll see some examples of that in later videos, link in the description. For today though, I just want to look at a quick and very simple example of a quotient group. So consider the additive group of integers. The cyclic group generated by 5 is a normal subgroup of the additive group of integers. We know that because we've previously proven, link in the description, that any subgroup of an abelian group is a normal subgroup, and the additive group of integers is an abelian group since addition is commutative. So any subgroup has to be a normal subgroup. This cyclic subgroup generated by 5 then, containing all the multiples of 5, is certainly a normal subgroup. Thus, we can construct the quotient group. So consider the quotient group of the integers by the cyclic group generated by 5. It looks like this. It contains all the cosets of the cyclic group generated by 5. That would be the cyclic group generated by 5 plus 0, which just contains all the multiples of 5, and then the cyclic group generated by 5 plus 1, which just contains all the integers that are 1 more than a multiple of 5, and so on. All the multiples of 5 plus 2, all the multiples of 5 plus 3, all the multiples of 5 plus 4, and you can probably see how these would start to cycle after this. If we consider the cyclic group generated by 5 plus 5, well, that's just going to look like this first group again. All the multiples of 5 will just be shifted forward to the next multiple of 5. In the end, it's still just going to be the set of all multiples of 5. Similarly, plus 6 would look just like plus 1, plus 7 would look just like plus 2, and so on. It works just like addition mod 5. In fact, we consider this quotient group to actually be the same as the group Z mod 5. And in general, we consider the quotient group of the integers by the cyclic group generated by n to be the same as the group Z mod n. You can see that this quotient group partitions the integers based on their values mod 5. If we were to take the plus 1 coset and add it to the plus 3 coset, that would equal the coset plus 4, which is just this one. Similarly, if we took an element from the plus 1 coset, like 1 for example, and an element from the plus 3 coset, like 3 for example, that'd be 1 plus 3, which would be 4, an element of the plus 4 coset. So you can think of this class of quotient groups as being the rigorous way to construct the integers mod n. They're all really just quotient groups, which are again homomorphic images of the containing group. So the integers mod n, that's a homomorphic image of the integers. And remember, the big theorem here is that these quotient groups, which are created by taking all cosets of a normal subgroup and using the operation of coset multiplication or coset addition, whichever it is, these are homomorphic images of the group G. So then you might ask, are all homomorphic images of G quotient groups? That's a big question, and we will answer that. But before we answer that big question, we're going to look at a few more examples of quotient groups. Links in the description. Let me know in the comments if you have any questions, and if you find these abstract algebra lessons helpful, please consider supporting Wrath of Math on Patreon. Link in the description. It's a huge help. Thanks for watching.